All right, welcome. We're going to talk about sketching curves using our pre-calculus and calculus knowledge together. So to start here, we'll talk about some things that you would want to do in order to sketch the curve of something. So we're going to talk about some guidelines here. These are guidelines. You don't have to do them necessarily in this order. Sometimes you don't even necessarily need to do all of these things if you can just sort of see it. But this is sort of how I think about sketching curves here. So one of the first things I do is I identify the domain of the function. That allows me to immediately think about candidates for asymptotes and discontinuities and things of that nature. The next step is intercepts. X-intercepts, Y-intercepts. Look for those things as well. Those are nice points. So those things are obviously very much pre-calculus. And even this next part is a little bit pre-calculus here, which is finding asymptotes. Perhaps now in this class you have learned that you should use a limit to find asymptotes as opposed to some tricks that maybe you learned in the pre-calculus or before that. But so asymptotes. And then this is where we get into more calculus-y stuff. The next thing you'd probably want to look for are local maximums and minimums. And along with that, it implies do it in red here, increasing and decreasing. So yeah, we use increasing and decreasing to help us find local maxes and mins. And then last thing, inflection points. And again, that comes from analyzing the concavity of our function. So those are my guidelines for trying to come up with a sketch of a curve of something that maybe you haven't dealt with before. Now, the example I'm giving here is something that we have dealt with before. So I gave something a little more familiar here. In class, we're going to do things that are a little less familiar to try to come up with. So let's talk about how we would go about finding a sketch of this thing here. So let's start with step number one, which is domain. Domain. So since this is a rational function, I know the issues that I might come into with this thing is that the denominator might be equal to 0. So that's how I'm going to find my domain, which is when x squared equals 1, so x is equal to positive or negative 1. Cool, so my domain is negative infinity to negative 1, negative 1 to 1, and 1 to positive infinity. Cool. Okay, next thing, we will find our intercepts. So intercepts is just when we're going to let y be 0 or x be 0. We'll do x being 0 first. So 2 times 0 squared over 0 squared minus 1. Well, that's going to end up being 0. So the point is 0, 0, which means that my x and y intercept are the same thing here. So both my x and y intercept are the point 0, 0. So this thing goes through the origin. That's good to know. And there's no other x intercepts that come out of this either. You can check really quickly and set this equal to 0. It'll only happen there. Sometimes with rationals, there's a couple of x-intercepts. All right, next one, asymptotes. Let's look at our asymptotes. So this is where we're going to use limits. Okay. Okay. So let's go ahead and take a look. And one of the things we want to do first, we'll do vertical asymptotes. So these things here are good candidates to look for. So I'm going to do the limit as x approaches negative 1 from the right. So if you remember, you can check the right or left. It really doesn't matter which one you do, of 2x squared over x squared minus 1. All right. Well, if we head from the right side here, we're going to end up with just 2 in the numerator. And the denominator is going to be approaching 0, but from which side? 0 from the let's see here, 0 from the, let's see, that's going to be -1. It's a little bit bigger than -1, which means that it's like negative 0.99999-ish number. Okay, so when you square that, that'll be less than 1. So this is going to be a negative number approaching 0, which means we're headed to negative infinity. Okay, so that means we do have a vertical asymptote at -1. And I'll check the other one as well, which was +1. Again, approaching from the right, it really doesn't matter which one you do. You might find they approach different things, but ultimately we're going to end up sort of seeing which way they're approaching from our sign analysis on the derivative when it's increasing, decreasing. So here, 1, a little bit bigger than 1, so like 1.00001. So this will be a positive small number, positive approaching 0. So that heads to positive infinity. Great. So I can conclude here that we have, let's see here, vertical asymptotes at x equals -1 and x equals +1. Cool. And then now let's go ahead and take a look at the horizontal asymptotes. So here we're going to do the limit as x approaches, we'll go positive infinity of x squared, 2x squared over x squared minus 1. Okay, so here is where we're going to use our strategy of multiplying by a fancy 1 and comparing it to the fastest growing function. So we're going to go ahead and multiply the numerator and denominator by 1 over x squared. So that's going to get us 2x squared over x squared over x squared over x squared minus 1 over x squared. Forgot the limit. Let me write that in. All right, so those divide, leaving us with 2. Those divide, leaving us with 1. And as x gets bigger, 1 over x squared heads to 0. So we get 2 as our... You'll notice that at no point did I consider that this was a positive value, x being positive. So if x was negative, this exact same thing holds true. So I'm not going to go through the work of showing the other one. You can. It's not necessary, though, if you recognize. So y equals 2 is our horizontal asymptotes. Cool. All right. And so now let's get into local maxes and mins. All right. Let's see. I'm going to have to organize my work a bit better here. That's fine. I'm running out of space as well. So let's go max min time. So maxes and mins. So first thing I want to do is take the derivative of this function. So that's going to be 4x times x squared minus 1 minus 2x times 2x squared all over x squared minus 1 quantity squared. Okay, and so that is going to be, let's see here, well, if we distribute this, we'll end up with 4x squared cubed minus 4x, and then multiply those together, and we end up with minus 4x cubed all over x squared minus 1 quantity squared. Those things will add to 0 in the numerator, so I've got negative 4x over x squared minus 1 quantity squared. Okay. So now let's go ahead and look for the places where the derivative is equal to 0. So that's just going to be when the numerator equals 0, which is at x equals 0. Let's also look when it's undefined, which is when the denominator is equal to 0. And we've already done this solving here earlier. It was part of our finding out the domain, so I know that x is both positive and negative 1. All right, so now let's do some sign analysis on this here. So negative infinity to negative 1, negative 1 to 0, 0 to 1, 1 to positive infinity. And then let's put in the factors here. So we got negative 4x, we've got x squared minus 1 squared, and that of course builds our y prime. Notice I put in factors and not terms, so not stuff being added, but stuff being multiplied or divided. All right, so since this is a negative here, anytime you plug in a negative x value, it will become positive. So positive, positive, but then switches over to negative. And then here it's being squared, which always will give us a positive value because we've already removed when it will be 0. So we have that y prime is positive, positive, and then switches over negative, negative. Cool. So I can add a line to the bottom of this as well and go, hey, what if we thought about what's happening to y? Well, it is increasing and increasing, then decreasing and decreasing. Which means that we have only one local value, local maximum or minimum. It's a maximum because we're changing from increasing to decreasing. So that's local maximum is y of 0, which equals 0. So our x-intercept / y-intercept is actually a local maximum, and we do not have any local minimum. All right. Okay. Well, I'm going to jump back up to here to do the other work because I've ran out of space down there, and I'm going to have to get another piece of paper in order to graph this thing here. So let's do our inflection points here. So let's find the second derivative. So I'll pick up where I left off down here and think about taking the derivative here. So y double prime is, so it's going to be negative 4 times x squared minus 1 quantity squared minus 2 times x squared minus 1 to the first now times 2x, so that's power rule and chain rule, times negative 4x, all over x squared minus 1 to the fourth now. All right, to proceed here, I'm going to factor out common factors. So looking at these two chunks of things, there's a negative 4 in common, and there's also an x squared minus 1 in common. So I'm going to factor that out. Negative 4 times x squared minus 1. So what does that leave behind? Well, in this first chunk of stuff, it only leaves behind one factor of x squared minus 1. And then over here, it's going to leave behind this minus 2, this 2x, and just x from there. This has been factored out, and the negative 4 has been factored out. So a couple things can happen here. First off, I have an x squared and an x squared in the numerator and denominator, so those will divide away. And I can simplify in here, because what I'll end up with is a negative 4x squared right here. So we'll have negative 3x squared minus 1. And that's hard brackets there, all over x squared minus 1 to the third power now. All right, so now that we've got the second derivative, let's figure out when is this equal to 0. Well, it's when the numerator is equal to 0. So let me solve for that real quick here. So we'll get negative 3x squared equals 1. So x squared equals negative 1/3. Oh, that doesn't have a solution. Something squared cannot be negative, at least not in the real numbers. All right, what about when y double prime is undefined? Well, we've already done this before. We know the jam, we know the game. It is positive and negative 1. So we only have one place we have to look when it comes to inflection points here. So let's go ahead and split up the number lines. So, two places to look. Negative 1 to 1, 1 to positive infinity. And let's list the different things. So negative 4, negative 3x squared minus 1, x squared minus 1 to the third, and that's all y prime, or y double prime, I should say. Okay. This is a little more cramped than I was hoping for, but it'll do, it'll do. All right, so here we go. -4 is always negative, no big deal there. All right, let's see, next one we got this. All right, so this function here is a parabola that's negative, and it's always negative is the thing. So there's no way to get it to positive, so that's negative, negative, negative. Here we got to be a little more careful now because it's cubed instead of squared, so it's not always a certain sign. So let's think about this. Turbo big negative number, cool. If I square that, it becomes positive, and if I subtract 1, it still should be positive, so that'll be positive. Here, if you plug in 0, you'll get -1 cubed, and that'll be negative. And then here, big positive number stays positive. So it goes from positive to negative to positive. All right. Now, let's again consider what does this mean for y. So if I were to extend this down and think about what does this mean for y, it means it goes from concave upward to concave downward to concave upward. However, this does not mean we have any inflection points because -1 and 1 are the locations of asymptotes. So those aren't inflection points. So I'll just make note, no inflection points though. Okay. So we've got all of our info here, and now we have to try to decipher what to do with it to help us graph it. So let me grab another piece of paper. And let's throw down some axes here. So let's go ahead and scale our axes here first. I'm just going to scale it by ones. There's nothing too scandalous about our values here. They're all about like 1s and 2s, it looks like. All right, so let's go ahead and start thinking about this. So we've got that the intercept is the origin, 0, 0. We also have that we got some asymptotes here. I'm going to put some dashed lines where they are. We got a vertical asymptote at -1, so dash, 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 at +1 as well, dash, 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 and a horizontal asymptote at 2. So put that in as well. Okay. All right, and then we've got a local maximum occurring at, what did we decide? 0, 0. So this is also the maximum. Some other things to note is that we are increasing in this region. I'll just write a little note, increasing. And then also increasing in here. Decreasing on the other side, though, and then decreasing over there. Something else is that we are also, let's see here, concave upward over here, concave downward in between -1 and 1, and concave upward here. Okay, so let's see if we can sketch this thing. So it should always be increasing over here, which means that it's going to follow along the asymptotes here and increase upward. Here, we're going to be following along the asymptote, increasing upward, but then it plateaus to create that maximum and then decreases over to this side. And then lastly, this is always decreasing, so if we were to go this way, it would be increasing, so it's this little part here. And there you have it. That is the graph of the thing we were trying to graph. Y equals 2x squared all over x squared minus 1. So those are the guidelines for graphing. We will do even weirder functions involving square roots, involving natural logs, things like that. So come prepared to tackle those. Take the survey, and I'll see you in class.